It is right above you tonight, whether you notice it or not. It has been sitting there, silent and unmoving, for over 4.5 billion years, older than the oceans, older than almost anything you will ever lay eyes on. It is roughly a quarter the size of Earth, close enough that you could fit every continent on this planet across its face and still have room to spare, yet far enough away that light from it takes over a second just to reach your eyes. For 50 years, scientists were confident about one thing above all else. It was finished changing. A cold, dead husk. No heartbeat, no motion, just a frozen leftover from the early solar system, quietly orbiting while everything else kept evolving. They were wrong. It is shrinking. It is cracking under its own weight. And in certain places, it is quietly shaking. Right now, tonight, while you are reading this sentence. That object is the moon. And here is the part that should make you sit up straight. NASA is preparing to send astronauts to live and work in exactly the region where this hidden activity is strongest. Stop and sit with that for a second. The site humanity has chosen for its next giant leap might not be nearly as still as we assumed. Before we go further, if you're new here, this channel exists to take the biggest, strangest discoveries in space science and break them down without the jargon, without the filler, just the facts and why they should matter to you personally. If that sounds like your kind of channel, go ahead and hit subscribe right now, because this story only gets stranger the deeper we go. Let's rewind to the beginning, because to understand how surprising this discovery really is, you first need to understand what people used to believe with total confidence. When the Apollo astronauts walked on the moon between 1969 and 1972, they left behind more than footprints and flags. They left behind instruments, seismometers, devices built to detect the faintest tremors traveling through solid ground, the same basic technology used to study earthquakes here on Earth. NASA's working assumption at the time was straightforward. The moon is small. It cooled off relatively quickly after it formed. A small, cold rock, the thinking went, shouldn't have much left going on inside it. No molten core stirring things up from below. No shifting plates grinding against one another the way they do on Earth. Geologically speaking, the moon was expected to be a corpse, a place where the seismometers would sit mostly silent, recording little more than the occasional meteorite strike. But the instruments didn't stay quiet. Over the years they operated, they picked up thousands of small tremors, and a handful of surprisingly strong ones. At the time, almost nobody knew what to make of the signals. The equipment was primitive by today's standards, the recordings were noisy, and once Apollo ended in the early 1970s, funding dried up and the moon stopped being humanity's top priority. In 1977, the seismic network was switched off entirely. The tapes went into storage, the missions moved on to other priorities, and an entire generation of scientists grew up believing the case was basically closed. Not silent, exactly, but settled, predictable, understood. The assumption that the moon was geologically dead mostly survived, untouched, for decades. It made its way into textbooks. It became the kind of fact nobody thought to question, the way you don't question that the sky is blue or that ice floats. Nobody expected reality to blow past that assumption so dramatically, decades later, using data that had been sitting quietly in storage the entire time. But it did, and it took new spacecraft, new software, and scientists willing to dig back through 50-year-old archives most of the world had forgotten even existed, to finally prove it. That is where the first real turning point of this story begins. The first major discovery didn't come from a human explorer at all. It came from a robotic orbiter, quietly circling overhead. NASA's Lunar Reconnaissance Orbiter, known as LRO, has spent years in lunar orbit capturing extraordinarily detailed photographs of the surface, some sharp enough to make out boulders the size of a car. And scattered across those photographs, scientists began noticing something strange. Thousands of small, cliff-like formations spread across the crust, sometimes only a few dozen feet tall but stretching for miles across the landscape. Geologists call them thrust fault scarps. Picture a giant bedsheet laid flat, then slowly pushed inward from both edges. It wrinkles, it buckles, small ridges rise up where the fabric has nowhere left to go. That is essentially what these scarps are. Wrinkles in the moon's crust, spots where the ground cracked and one side got shoved up and over the other. Here is why that detail matters more than it sounds. Wrinkles like these do not form on a body that has finished changing. They form when something is actively squeezing the surface from the inside out, over and over, across long stretches of time. And what is doing the squeezing, researchers now believe, is the moon itself, slowly cooling from the inside, slowly contracting, shrinking the way a grape shrinks into a raisin over unimaginable spans of time. Not violently, not dramatically, at least not on human timescales, but steadily, continuously, and apparently still happening today. For a viewer standing outside tonight looking up at that pale disk in the sky, that single fact reframes everything. It isn't a dead rock. It's a body still settling into old age, billions of years into its life, and still, somehow, on the move. But none of that prepared anyone for what came next. The second beat is where this story gets personal, because it connects those cliffs directly to real, measurable shaking underfoot. Scientists went back to the old Apollo seismometer data, recordings most people had written off decades earlier as historical curiosities, and reprocessed them using modern analysis tools, techniques built to squeeze far more precision out of sparse, aging signals than anyone in the 1970s ever could. What they found was startling. Some of the strongest shallow moonquakes ever recorded by the Apollo instruments appeared to trace back to the lunar South Pole region, the exact same area riddled with those young, freshly formed fault scarps. One of the most powerful shallow moonquakes on record originated somewhere near that pole, though pinning down its precise source proved extraordinarily difficult because the Apollo seismic network was so limited and so sparsely spread across the surface. Even with modern relocation techniques, researchers could only narrow the epicenter down to a wide cloud of possible locations, not a single confirmed point. Still, the pattern itself was hard to ignore. Fresh cliffs, clustered tightly together, sitting almost directly on top of the source of genuine, ground-shaking seismic events. Why should any of this matter to you, watching from a planet 238,000 miles away? Because that exact region, the lunar South Pole, is the region NASA has chosen as the destination for humanity's return to the moon, not the flat, calm plains where Apollo once safely touched down decades ago. The rugged, shadowed, resource-rich South Pole, selected specifically because permanently dark craters there may hold frozen water, water future astronauts could one day drink, use to grow food, or even convert into rocket fuel for missions deeper into space. The single most valuable stretch of real estate on the entire moon might also be sitting on some of its most geologically active ground. That realization leads directly into the third and biggest twist in this story. In January 2024, a team led by planetary scientist Tom Waters of the Smithsonian Institution published a study that connected all of these threads directly to NASA's Artemis landing plans. His team didn't stop at simply mapping faults near the candidate landing zones. They built models simulating what would actually happen if one of those faults slipped again, how strong the resulting shaking could get, and what it would do to the loose, dusty ground astronauts might be standing on at the time. Waters put it about as plainly as a scientist ever will: 1-to-1, 2-to-1, 5-to-1, 9-to-1. Our modeling suggests that shallow moonquakes capable of producing strong ground shaking in the South Polar region are possible from slip events on existing faults, or the formation of new thrust faults. Read that again slowly. That is a scientist saying, in careful, measured language, that the ground in this region can move, and that it might move again, without warning, at any time. It gets more specific and more concerning from there. The researchers modeled one particular fault scarp sitting inside a location called Degirliche Rim 2, one of the actual candidate regions NASA identified for a crewed Artemis landing. Their simulation showed that the original formation of that fault could have been associated with a moonquake roughly equivalent in strength to a magnitude 5 earthquake here on Earth. That might not sound catastrophic by Earth standards, where our buildings are engineered with decades of seismic codes behind them. But on a world with no atmosphere, no reinforced bedrock foundations, and where astronauts may be relying on lightweight habitats, delicate life support systems, and fragile solar arrays, a magnitude 5 shake is far from nothing. The same modeling found that some slopes across the South Polar region, including slopes inside the very permanently shadowed craters holding that prized water ice, could be vulnerable to landslides from even light seismic shaking. The darkness that has preserved billions of years of ice may also be hiding unstable, crumbling ground. Sit with that for a second. The place we are going specifically for water might also be the place most likely to shift under our own boots. If that thought is unsettling you a little, good. That means it landed. Hit like and drop a comment telling me honestly whether you'd still want to be one of the first astronauts standing on ground that scientists openly admit they cannot fully predict yet. I read every comment, and I genuinely want to know whether this changes how you feel about the Artemis landing sites. Now here is where the human side of this story deserves real attention, because behind every one of those data points sits decades of frustration, patience, and quiet uncertainty. The Apollo seismometers that made all of this possible were only active for a handful of years, from the early 1970s until that 1977 shutdown, when budget cuts brought the entire program to a close. The scientists who eventually revisited that data decades later weren't working with clean, modern instruments. They were working with faint, decades-old signals recorded on outdated hardware, transmitted across 250,000 miles of empty space, then archived and largely forgotten for nearly 50 years. Locating the true source of a moonquake using a sparse, aging network like that is agonizingly difficult. Even for the strongest quake in the entire dataset, researchers still could not pin down one exact epicenter. All they could produce was a wide fog of probable locations draped across the South Pole, a haze of uncertainty that modern tools could narrow but never fully resolve. And then there was the waiting. Waiting for LRO to spend years quietly photographing the surface before anyone noticed the pattern of scarps hiding in the images. Waiting for someone, somewhere, to have the idea to connect two completely separate datasets, collected decades apart by entirely different missions into a single unified picture. Wading through the slow grind of peer review, funding proposals, and building the right team with the right mix of expertise, planetary geologists who understood the scarps, seismologists who understood the old Apollo signals, and engineers who could translate all of it into something useful for mission planners. None of those specialists could have solved this puzzle alone. It took years of quiet collaboration, cross-checking, and second-guessing before the team felt confident enough to publish anything at all. There is no dramatic breakthrough moment in this story, no single afternoon where someone shouted Eureka in a lab. Discoveries like this one are almost never a single lightning bolt moment. They are years of unglamorous, painstaking work carried out by people with no guarantee their questions would ever be answered, sifting through noisy signals and grainy photographs long after most of the public had stopped thinking about the moon at all, done specifically so the astronauts who eventually walk through that region will know just a little more about the ground beneath their boots than the scientists who first raised the alarm ever did. Which brings us to right now, because none of this is ancient history, it is unfolding in real time this very year. In April 2026, NASA flew Artemis 2, sending a crew of astronauts around the moon for the first time since the Apollo era, a critical shakeout test of the very systems that will eventually carry humans back down to the lunar surface. As of 2026, NASA has restructured the road ahead. Artemis 3, once billed as the mission that would finally put boots back on the moon, has now been redefined as a demonstration flight scheduled for 2027, one focused on testing the docking between the Orion spacecraft and the commercial lunar landers being developed separately by SpaceX and Blue Origin, essentially a dress rehearsal for the real thing. The actual crewed lunar landing has now shifted to Artemis 4, and NASA continues to target early 2028 for that historic touchdown, still aimed squarely at the same South Polar region flagged by Waters and his team as geologically restless. Engineers and mission planners are, at this very moment, weighing exactly the kind of fault and landslide data this study produced as they work to finalize precisely where astronauts will eventually set foot. Meanwhile, the hardware itself is visibly coming together. Through the first half of 2026, NASA rolled major sections of the SLS rocket core stage out of its assembly facility in Louisiana, stacked components inside the vehicle assembly building in Florida, and ran launch countdown simulations with the very team that will eventually send Artemis 3's crew into orbit. In June 2026, NASA formally announced the astronauts assigned to that upcoming test flight. Every one of those milestones is a small, concrete step toward the moment engineers finally have to commit to a specific patch of ground near the South Pole and say with confidence, this is safe enough to land on. Mark this down because it is specific and it is coming. NASA is targeting early 2028 for the first Artemis crewed lunar landing, the first time human beings will stand on the surface of the moon in more than half a century, and the first time anyone will do it inside a region scientists now know is still tectonically alive, not a possibility. Not a maybe. An inevitable, unprecedented moment already being built toward, piece by piece, rocket stage by rocket stage, hardware test by hardware test, happening right now while you watch this video. Zoom out for a moment because there is something bigger going on here than fault lines and old seismometer tapes. For nearly all of human history, the moon stood as a symbol of permanence. It rose, it set, it waxed and waned in the same predictable rhythm night after night, generation after generation, empire after empire. Ancient farmers timed their harvests by it, sailors navigated by it, poets wrote about it as though it were the one fixed point in an otherwise uncertain universe. It was the constant overhead while everything below it changed, rose and fell. And now we know that even the moon, steady, silent, seemingly eternal, is still slowly transforming, still cracking under its own weight, still finding new ways to surprise the species that once assumed it fully understood that pale light in the sky. Maybe that is the real lesson buried inside this story. Nothing in this universe is ever truly finished settling. Not planets, not moons, not, if we're honest, us. We keep returning to a place we thought we already knew everything about, and it keeps having secrets left to tell us, decades after we first believed the story was complete. Humanity looked at the moon for thousands of years and called it finished. It took less than 60 years of actual investigation to prove that finished was never the right word for the moon, or maybe for anything we think we fully figured out. And that is the uncomfortable, thrilling truth this story leaves us holding. We still do not actually know how tectonically active the moon really is. We do not know how many more of those fault scarps are quietly forming right now, hidden from every camera currently in orbit. We do not know whether this slow shrinking will continue at the same gentle pace forever, or whether it could accelerate in ways nobody has modeled yet. We do not know with any real precision whether a future Artemis crew will actually feel the ground shift beneath their boots, or when that might happen, or how strong it could be if it does. The moon kept this secret for over 4 billion years. It only told us because scientists finally went back and asked the right questions with the right tools at the right moment. Which raises the obvious, unsettling question this field still cannot answer: what else is that quiet, familiar disk in the sky still not telling us? If this story pulled you in, subscribe and turn on notifications so you don't miss what comes next in this series, because the deeper we dig into Artemis, the stranger the moon keeps getting. Drop a comment and let me know what you think NASA should do with this fault line data before Artemis 4 ever attempts to land. Share this video with someone who still thinks the moon is just a boring dead rock hanging in the sky. They need to see this. And next time, we're going even deeper into the story, the untold history of the water ice hiding inside those permanently shadowed craters, and why some scientists now suspect it might be far harder to safely reach than anyone originally imagined. You will not want to miss it.